And we now need to define therefore what is it that we can consider as logic 0 and logic 1. Okay. So, for this let us go back and see, with the inverter I give V in, and like in the analog noise case I will add 20 millivolt of noise. Okay, this is logic 0. So, this is supposed to be logic 0, okay, and let me call it 0 volt. Okay. Now, I will plot the voltage transfer characteristic again here. I will draw it again. V in, V out. Okay. Remember, the ideal characteristic was going to be something like this. Okay. And the black curve is the practical case. So, this is VDD by 2 and this is VDD. So, what I am saying is, I have fed an input to this inverter, I will write it in magenta, V in, which is logic 0. So, this is my V in, 0 volt. Okay. Now, if I give 0 volt to this inverter, the voltage transfer characteristic simply tells me that whatever value of the curve I get, that will be my output. That means V out equal to VDD. Okay. Now, instead of V in, I give plus 20 millivolt of noise because of some random source of noise. I do not know what it is. I can have arbitrary noise. I give plus 20 millivolt. I want to see what output will I get from this inverter, right. So, remember in the analog case 20 millivolt changed your output significantly. Okay. So, instead of 0 millivolt, I am going to give 20 millivolt here. So, what is the output of the inverter? Simply look at the value of the curve at this point. It is also equal to VDD. Fundamentally, this is the advantage of digital processing. It gives you robustness to noise. Now, what if I gave noise of 30 millivolt, 40 millivolt? It looks like almost near VDD by 2 I can go, right. I am drawing this not to scale, right. So, this could even be 1 volt of noise. So, even if you give 1 volt, okay, 1 volt is 20% of the supply range, 5 volts, right. If I give 1 volt of noise, I am still getting an output which is nearly VDD. This is never possible in the analog domain. Okay. So, fundamentally, I can already see that there is a range, even in the practical case, which I can consider as logic 0, input logic 0, and there is a range which I can consider as input logic 1, okay, where the output is guaranteed to be VDD, I mean very close to VDD, right. So, the question now is, I want to find on this voltage transfer characteristic two boundaries. Okay, in green, anything below this from 0 volt is logic 0, input logic 0. Then I will not use purple, I will use purple actually. On the other side, I want to define another boundary which goes all the way to VDD. This is logic 1. Okay, I don't know what these values are. So I'll just call this guy as Vx and this guy as Vy. Okay, or I could give it a more meaningful name. It is the boundary up to which I want to consider the input as a logic low and a boundary after which I want to consider it input as a logic high. So therefore I will call this as VIL and this point VIH. Okay. So now what I want to do is I want to find out on this voltage transfer characteristic where should it be, right? For example, should I say 0 to 20 millivolt is logic 0, or should I say up to 1 volt is logic 0, or can I say up to 2.5 volt VDD by 2, right? So why not VDD by 2? Why can't I say VIL equal to VIH equal to VDD by 2, right? We have to now figure out what is the point that actually determines logic low and logic high appropriately. Okay. So now let us look at this case that we had a little more closely. Okay. What it did was it actually killed that noise for us. If I get 20 millivolt of noise, it simply killed the noise for us. Okay. Now instead of 20 millivolt, let me take the voltage transfer characteristic curve again. V out versus V in. I'll draw it slightly exaggerated now, okay. And let us say that I have an input which is nearly VDD by 2. Okay, this is VDD. Let's say the input, I am now giving an input V in equal to VDD by 2. Okay. So what is the output of this guy? Actually this would be nearly VDD by 2. Okay. Now let us say that I give a 20 millivolt noise to the input. So instead of this I will give plus 20 millivolt. So what will happen now? Input has increased by 20 millivolt and therefore it would be somewhere here. So if I give plus 20 millivolt, my output may have fallen somewhere near VDD by 4. It would be less than VDD by 4. Something very small. If you give 30 millivolt, it would fall even further. Right? So now what this is telling you is that in this region, right, somewhere close to VDD by 2, if I give a small noise, it is altering my output significantly. Okay. Now instead of plus 20 millivolt, if I give minus 20 millivolt noise, now noise is random, it could be plus or minus. Instead of this, if I give minus 20 millivolt, then what will happen? Your input will appear here. This is minus 20 millivolt. VDD by 2 minus 20 millivolt. Then the output is actually here, greater than 3 VDD by 4. If I give minus 30 millivolt, it would be here. It would be much closer to VDD. So what you are seeing is, if the input V in is somewhere at VDD by 2, positive noise could take the output V out closer to logic 0, negative noise could take the output closer to logic 1. Okay. So effectively what is happening in this case is the noise is getting amplified. Okay, the noise is getting amplified, and therefore the output can completely go haywire, right? So what we want to do is to operate in a region for both logic 0 and logic 1 where the noise will get killed. Now, what does the noise getting killed mean? It means that a small change, right? So if you go back to this earlier case that we had considered, right, where I had shown the, let me just show you that. Now on the other hand, like I told you, if I operated this guy here, right, V in equal to, let's say, 100 millivolt. Now even if you give plus minus 20 millivolt noise, it doesn't matter, the output will still be VDD, right? You could change, so this will be V in plus 20 millivolt, V in minus 20 millivolt. If it is 100 millivolt, any change, positive noise, negative noise, it does not change the output. The output is still logic 1. It is close to VDD. Okay. So therefore, what we are saying is we want to operate in a region for both logic 0 and logic 1 in a place on this voltage transfer characteristic where the output is not susceptible to noise. That is, the noise should get killed. The noise gets amplified in a region where the gain is very high. What is the gain? It is actually just the derivative of this curve. So why did in this region, why did the output not react to the noise? It is because the output is flat with respect to Vin. So here, if you look at it, dV out by dV in equals 0. Likewise, if I had operated my V in here, okay, V in close to, okay, let's say VDD is 5 volt for example, plus minus 20 millivolt will not matter because on the voltage transfer characteristic the output will still remain at 0 volts, at least nearly 0 volts. So therefore, plus minus 20 millivolt is getting killed there also. Here again the gain is dV out by dV in equal to 0 because the output is constant for a range of inputs. Whereas here the gain is maximum and negative, forget about the negative part, but it is maximum. So even a small noise is getting amplified and appearing at the output and tampering with the output, and therefore I cannot define my VIL and VIH, right, that boundary to be at VDD by 2. I have to split it and define it differently for low voltages and differently for high voltages. Okay. So therefore, now I need to, having gained some insight into how the derivative of this curve actually determines the reaction to noise, what we need to now figure out is where should I go ahead and place my VIH and VIL. So V in, V out, again I am going to draw this slightly exaggerated, okay. It is not so exaggerated in reality, I mean VDD, right, this is somewhere near VDD by 2. So now the question, like I told you, is where should I go ahead and place my VIL? Should I place it here? Sorry, right, or should I place it close to VDD by 2? So the answer to that question really comes from what we had discussed just now. We want to place it at a point where the noise gets killed. That means the gain should be less than 1. Okay. So we want to place it VIH and VIL should be at points on the VTC where noise is suppressed or killed, implies the gain, which is the derivative, right, should be less than 1. The modulus of the gain should be less than 1, because in that case V out will be gain times the change in input, right. So what we are saying is V out is dV out by dV in into delta V in. Okay, this is what we are saying. And if the dV out by dV in is very less, close to 0, then it will not even react to the input noise, right. This is my noise. We want that delta V out to not react to the input noise. So what should we do? We got to place it at a point where the gain is actually, modulus of the gain is less than 1. The limit is therefore the point at which the gain is exactly minus 1. Okay. So here, so you identify 2 points on this curve where dV out by dV in equals minus 1. Out here also dV out by dV in equal to minus 1, and then you plot this 2 things. Okay. So this is VIL, VIH. The corresponding outputs on the y-axis corresponding to VIL is called VOH, and corresponding to VIH you have VOL. Okay. So you define on these voltage transfer characteristics these 2 points where the derivative is minus 1. Okay. Of course, the modulus of the derivative is just 1, right. What we are saying is the gain to the left of VIL is significantly less than 1, gain to the right of VIH again is significantly less than 1, and the noise will get killed in both those regions. In between, the noise will get amplified. Okay. So what we are now saying is, if V in is greater than 0 but less than VIL, you can treat it as logic 0. If V in is greater than VIH less than VDD, you can treat it as logic 1. And the beauty is they will be logic 0, logic 1 in spite of noise. In spite of noise. Okay. And therefore digital computations are extremely robust to noise, and that's why they are so popular. In fact, if you look at the effort taken to do analog computation versus digital computation, the effort is much higher in digital computation. You have to first of all sample this, you have to time quantize, you have to amplitude quantize, put an ADC, get it into a digital computer, then binarize it, get it into a digital computer, and then operate on it. Why do all this? Because it is robust to noise, for this reason. Okay. So having now defined these 2, right, we have an obvious question to ask. What happens if the input lies in this region? I would say greater than VIL but less than VIH. this region is indeterminate. Okay. So the point is, if I apply an input here, right, you might think that you will get the output here. Okay, this is the VIN, right, you might get the output here. That's what the voltage transfer characteristics tell you. But the fact is, the moment I apply some noise, right, that output can either go to 0. If you apply a positive noise there, it will go to, output will go to 0. If you apply a negative noise, output will go to 1. Okay, so really this is an indeterminate region. Indeterminate region. Why? Because the output now depends on the noise. In these two regions, in logic 0, logic 1 region, in spite of noise, my output is still consistently logic 0 or logic 1. Okay. But the indeterminate region, the output is determined by the polarity of the noise, and therefore it could be 0 or it could be 1, and therefore it is not consistent, it cannot be used. The input should not be given in this region if you want to operate it as a logic gate. Okay.